Okay, so I wrote down another example here. I did this off camera just because it takes kind of a while, and when I'm writing down little things, my hand tends to get in the way, so I could just point at this one. So this is an example of an infinite ordinal in the subscript here that we did before. So a phi sub omega and the first fixed point of that function here. So it gets a little crazy, but I always sometimes like to see a more complicated example just to you can kind of try it on your own and see if you get kind of the same result. So there's a couple steps that I kind of skipped over. But basically what I'm doing here is I'm doing the diagonalization. So I diagonalize the 3 here, end up with phi sub 3. You keep the inside function. You minus 1 from the inside, add it to the outside to escape the fixed point trap. I broke this apart into 3 copies of the previous phi 2 function, kept 2 here, broke 1 off, then kept the inside function minus 1 from here, add it to the outside. And then I kept on doing this kind of thing, so I'd break apart the inside function here, so phi 2 turns into 3 copies of phi 1, keep 2 here, break 1 off, minus 1 from the inside, add it to the outside. Do the same thing. I broke apart this phi 1 into 3 copies of phi 0, kept 2 here, broke 1 off. And the same thing kind of happened here where I had this whole thing plus 1. I used the rule of exponentiation or whatever. So let's say, for instance, like omega to the a plus 1 turns into omega a times omega. So this whole thing here turned into this times omega. I diagonalized to turn it into a 3. So I have this whole thing times 3. So I keep 2 here, and then I add 1 to the end. And now this whole thing here, basically, this here would have been in a phi omega to the 0. So I'm allowed to just diagonalize that. So turn that into phi 3 of 0, which I broke apart into 3 copies of phi 2. And then I broke apart that one phi 2 function into 3 phi 1 functions. And this is kind of where I skipped ahead a couple spots. I turned the remaining phi 3 copies of the phi 0 function into omega to the omega. We did that before. And then I kind of just did some arithmetic to expand that out so we can work on it some more. So that turns into omega squared times 2 plus omega squared plus 3. And then I just took this last little bit here. So I didn't write down this whole thing. I wrote down the last part of this equation. And basically what I did was I just took this one step further. So I took 1 copy of the phi 1 function, broke that apart into 3 phi naughts, kept this on the inside, minus 1 from the inside, so this turns into a plus 2, and added it to the outside. So you can kind of picture this would keep on expanding and expanding and expanding out into a bigger and bigger equation, basically. And this whole thing, if you wanted to evaluate it, you'd have to stick this into the subscript of the fast-growing hierarchy. So you can kind of see, at this point, it kind of just becomes like an academic exercise. You'd never really be able to plug this whole function into the fast hierarchy to see what you would get, whatever. You really only do approximations. The function itself just becomes way too big to do. But still, it's good to do this just to see that we have consistency, to see that we're able to do it if we want, whatever. The whole thing is, it's very, very consistent, and we know that it works, and we can use it to create much bigger ordinals in a systematic way, type of thing. So we can keep on going with this. If we can get to omega in the subscript, there's no reason why we can't do omega plus 1. Let's just erase all this nonsense here. And I'm just going to keep these rules on the side here, just because they're good to have, they're good to look at in case we ever need to use them. Eventually you want to get to the point where you kind of memorize them, just so when you're doing the arithmetic it's kind of like second nature, but in the beginning it's good to have them there. So we can do stuff like phi omega plus 1. And we'll just do of 0 just to make it easy. Diagonalize to 3. And how we would do that is we just very simply do 3 copies of the previous phi function. So this would turn into phi omega 3 of 0. So we could do phi omega of phi omega of phi omega. And this last omega we could diagonalize. So this would turn into this, whatever, basically. So that's how you break apart that. And this goes to something that we already know how to do, whatever. This could turn into 3 copies of the 2 function, you can break one off, turn it into 3 copies of the 1 function, blah, 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 blah. So we can keep on going like this. We can do phi omega plus 2, phi omega plus 3, omega times 2, omega to the omega. We can stick like an epsilon naught in here if we wanted. Make something really big, which would just get diagonalized to omega to the omega. And we can even do phi to the phi to the whatever, anything in here, it doesn't matter. We can do phi to the phi to the phi. Okay, well this is kind of interesting because this is kind of the same thing that we had when we had infinite towers and infinite nestings of epsilons and zetas and whatnot. So what if we kept on going with this? What happens? I don't know why I keep on erasing this. I just, it's easier for me to write up here than like down here and whatnot. Okay, so if we have an infinite nesting of phis, what do we get? This is 0, 0. Okay, well this is another infinite ordinal, a gigantic infinite ordinal. This is called gamma naught. And this is as far as there is like a systematic way of doing things where everybody kind of does it the same way. After this, everyone kind of has their own way of doing things, and we are going to go far, far, far beyond this just because we can. And but this is a really, really good point of interest. This is the infinite nestings of Veblen functions, basically. So how would we evaluate something like this, gamma naught? What if we had, like, in the fast-growing hierarchy, gamma naught of 3? Well, basically, in a similar way that we evaluated epsilon naughts by doing repeated a tower of omegas, this many high, or this many minus 1, whatever it was, we can do the same thing, whatever. So we can do the number of phi functions is this number here. So if we were to diagonalize this, this would turn into f sub phi, sub phi, sub phi of 0, of 0. And then this would be of 0, this would be of 0, this would be all of 3. So it gets a little bit confusing because you have to plug in the numbers of each function, because each function has an input that you have to put in. And for this reason, this is not, it's indeterminate, because this is kind of like a function of functions. So this is the first indeterminate ordinal that we reach, which is another kind of interesting property of it. So if we were to evaluate this, what would it turn into? So we know phi 0 of 0 is equal to 1, so we can plug that one in. Phi 1 of 0 is our epsilon series, so we have epsilon naught, so let's just rewrite that so it's not so messy. F phi of epsilon naught of 0, 3. We diagonalize this epsilon 0 to get f phi epsilon, phi omega to the omega, and we can diagonalize that omega to a 3, so we end up getting phi omega to the 3 of 0, and diagonalize that at 3. Let's go up here now. And we know that we can break this omega 3 using ordinal arithmetic, so we can do f phi of omega squared 2 plus omega squared plus 3 of 0 of 3. And basically this is going to break apart the same kind of way that we did before. We can do multiple copies, so whatever number we have in here. So we can do 3 copies of the previous phi function and then go on breaking it apart like this. So let's break this into 3 copies of omega squared 2 plus omega squared plus 2, and break that one into 3 copies of the previous one. So you'd end up getting something like this. So you end up getting f of phi, let's do 2 copies of omega squared plus omega 2 plus 2. And the reason why I have 2 here is because I originally had 3 copies of the previous function, but we're going to keep 2 and break one off so that we can break that one apart into 3 copies of the next one. So you'd end up getting like 2 copies each of a cascading down of this function here. So the next one would be 1, next one would be 0, or just omega squared times 2 plus omega squared, blah, 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 blah. And we keep on whittling this down until eventually we get down to 3 copies of omega of 0. And then from here we know where to go, basically. So you have a whole bunch of functions all piled together. And this is a really, really, really massive, massive, massive number, because all these functions are functions within functions. So you have to evaluate the inside before you even think about getting and starting to whittle down the outside functions. So it really, really blows up. And we can even go beyond that. We can go gamma naught plus 1. So what would gamma naught plus 1 equal? Let's see. What if we had f gamma naught plus 1? Let's do it. Well, this is really simple. This is just our basic fast-growing hierarchy operation here. We just do 3 copies of the fast-growing hierarchy, the previous function. So this would be 3 copies of the gamma naught function. So f gamma naught of f gamma naught of f gamma naught of 3. All right, so f gamma naught of 3 is gigantic. It's huge. It's bigger than anything we've done so far. And we plug that into here. So this becomes a cascading of phi functions that's this big. And then we evaluate that. And what is that? Who knows? It's monstrous. Absolutely monstrous. I'm running out of adjectives to say how big these numbers truly are, but they are very, very big. And then, of course, then you figure out whatever that number is somehow, and then you plug that into the number of cascading phis in that function. So we can keep on going. You can always add 1. No matter how big the ordinals get, you can always add 1. So there really is no limit to this. The limit is really based on like the systematic ways that you can come up with for doing this, so it doesn't just become arbitrary. So you're not just saying like, oh, plus a million, billion, whatever type of thing. You always want to have a systematic way of doing things. So we can go further. Like you can do the same thing. You can take gamma to the omega. You can take gamma to the epsilon naught. You can take gamma to any of the ordinals that we've created so far. You can do gamma. What's it called? To the phi of whatever. One important note though is you might have figured this out already, but I'm gonna stop erasing this. I'll just write it underneath. Gamma naught satisfies the equation phi of A is equal to A. Because you can kind of see that, like if you have an infinite cascadings of phis or whatever, and you put another phi in the beginning or whatever, it's not going to do anything. It's going to equal the exact same thing. So that satisfies this equation basically. So how do we get to something like the subscripts of the gamma naughts or whatever? Like what if we had gamma naught of 1 or whatever? I really should have explained that before I started saying that you can plug all these things in. So let's do that. What would gamma 1 be? So in the same kind of way that we have epsilon 1 and epsilon 2 and zeta 1 and zeta 2, gamma 1 works in the exact same way basically. So we have an infinite cascading of phis, and we just stick gamma naught and then add 1 at the end. So we do the exact same thing. We use the 1 to escape the fixed point trap, basically. And if we wanted to, so this is gamma 1. And if we wanted to diagonalize that, basically, so gamma 1 diagonalized to 3 would just be 3 copies of the phi function with gamma naught plus 1. And then each one of these is the 0th fixed point, whatever. So kind of the same type of thing as when we did epsilon 1 or zeta 1 or whatever. You just do the 3 copies of the function, whatever, and then you just add the 1 to escape the fixed point trap. So same basic thing. Now to go beyond this or whatever, it gets a little bit weird. You end up running into the same kind of problem, because then you can do a gamma to the gamma to the gamma, blah, blah, blah. You can find out the fixed point of that, and infinite cascadings of gamma naughts is something called the Ackermann ordinal, and you could write another thing, let's call it alpha or something like that. And then you could do an infinite cascading of that, blah, 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 and then call that something else. And we run into the same problem of basically needing an infinite number of Greek letters to enumerate all these fixed points, basically. So you can start doing multi-argument Veblen functions. And basically what this is you know how we had phi A of B? Well, basically we're just going to rewrite this. So we do phi B of A. So we stick this one over here and this one right here. And you could do it the other way around. You could do A and B if you really wanted. I mean, there's no really standard way of doing this. I'm just used to this way, so that's how I'm going to do it, basically. But if you want to do it the other way, you can. Just stay consistent. Make sure you do it the same all the time. And the reason why this is beneficial when you get to things like gamma naught is because then you can add arguments to this inside here. So gamma naught in our extended Veblen function is going to be phi 0, 0, 1. So now we have a way of writing this without having to write down a whole bunch of phis or whatever. It's just a much easier way to write this with one function, basically. And the way we were to write gamma 1 would be a 0, 0, 2. So basically, gamma A is going to equal this three argument Veblen function with A plus 1 at the end here, basically. And remember that you can have any number you want in here, or whatever. You could have like a phi something in here, or an epsilon naught, and you can have a 3 here. So you can have all possible combinations of things in here, or whatever, and that would equal a real infinite ordinal. So you could do anything you want, whatever, but this is just a different way of writing this. So this is the 3-argument Veblen function. And if you wanted to go beyond this, whatever, so let's say we had that Ackermann ordinal that I was talking about. So the limit of gamma to the 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 infinite, what we do is we add another argument to the Veblen function. So we have, for the limits of the gammas, gamma, that's going to equal a Veblen function with 4 arguments. So that's going to equal this. And this is also known as the Ackermann ordinal. And you can keep on adding arguments arbitrarily, and you can keep on going like that. But there's, once again, a better way of doing this, a way to write this down in a single function or whatever. And this is called infinite collapsing ordinals. But I'm definitely going to leave this to the next video because this is already going pretty long. See you next time.